Here we have a really nice calculus problem that asks for the intersection volume of two cylinders. At first glance, the problem may seem very complicated. However, a little visual analysis will help us to find an easy and elegant way to tackle this problem. We are given two concentric and identical rectangles, and one is rotated with a 45-degree angle. Their bases are 2, and heights are 2 plus 2 times square root of 2. If you ask why I chose this specific height, you can draw an imaginary octagon around these rectangles with a side length of 2. From top, you get 1 square root of 2, at the middle, you get a 2, and you get 1 square root of 2 at the bottom as well. Notice that the intersection of these rectangles creates a parallelogram. For now, remember that this will play a crucial role in our solution. I want to name the height of this parallelogram h sub p and base b sub p, p standing for parallelogram. We all know area is base times the height, and I also want to note that b sub p is equal to square root of 2 times h sub p because h sub p is basically the width of the rectangle. By looking to the top left blue triangle, you can notice it since we know it's a 90, 45, 45 degree triangle. Now, we rotate these rectangles around themselves to form cylinders with radius 1. To understand how the intersection area behaves, we can also create rectangular planes that are parallel to the both base rectangles and their width is similar to the width of the circle at the given height. Let's see how it goes. From the animation, we can observe that the intersection area of these rectangles will always be a parallelogram, getting smaller and smaller while scanning the intersection volume. Does this ring a bell for you? How can you set up an integral to solve this? Remember the variables h sub p and b sub p from earlier on? Maybe writing them as a function of h will help. Please pause and think for a moment. I hope you had a moment. I will integrate the area of these parallelograms with respect to h, and the h will be a tiny nudge in the z direction, representing the height of very, very thin parallelograms. And multiplying the h with h sub p times b sub ph will give us the volume of infinitesimal volume of any very thin parallelogram. If we integrate this with h going from 0 to 1, it'll give us the upper half of the volume of the intersection. Therefore, we place a factor of 2 in front of the integral. Now, let's define the base and height functions of this parallelogram. Since r is always 1, we can use the Pythagorean theorem to write the following equation. Let's solve this for h sub p. After that, we can substitute this result into our original integral. But what about the b sub p function? Earlier, we defined b sub p as equal to h sub p multiplied by the square root of 2, due to the 45-degree angle. Think about it. If these cylinders were intersecting at a 90-degree angle, both h sub p and b sub p would be equal, forming a square. The 45-degree angle just makes the problem appear more complicated. Let's substitute this expression and simplify the integral. Now, we can easily integrate this using the power rule of integration.